Welcome to today's Tech Talk. I'm very excited to have Will Arnold here with us to talk to us about the structural engineer's role in addressing climate change, particularly around embodied carbon. This is the first part of a two-part series. Next week, we'll be hearing from Tessa Brunette and her team at Arup about research they're doing through Africa in terms of embodied carbon studies. Will is the head of climate change at the Institute of Structural Engineers. Previously, he was a structural engineer at Arup, working on some pretty cool buildings and structures. And he's been with the ISTRUCT for a few years now, I think, leading their response to the climate emergency and focus on sustainability, really, in terms of structural engineering. He's passionate about driving change within the profession, helping us set minimum standards for the Institute and for the profession as a whole, and does a lot of work producing publications around sustainability and climate change. He is chair of the Construction Industries 2050 Working Group, an active member of the EDGE think tank, and part of the UK Built Environment Advisory Group, as well as the Engineering Advisory Group. So he does a lot of work in this space, and I think is fairly well versed. With that, thank you, Will. I'll hand over to you.
Okay, thanks very much. And thank you everyone for taking time out your lunch to listen to me speak today. I'm gonna put my slides up. And I've got a couple of slides to introduce myself. And then actually there's a very short sort of video that I wanted to play at the start. It's only a few minutes. Just before I get to that, it's worth noting that this is kind of part one of two. So whilst today I'm going to speak around embodied carbon and net zero and what that means from a very high level point of view, the next technical talk is Tessa Brunette, who's based in South Africa, who's been part of a big piece of Arup research into looking at embodied carbon factors from across 5 different African countries, and is going to present on what we can do with that, the takeaways and findings from the research, and how she's been able to put that into practice on her own projects. So I consider myself the scene setter for her talk, and I really hope that you can all join her talk next month. Yeah, by way of quick background introduction to myself, I spent about 10 years at Arup. I did all sorts of things from fairly standard commercial office buildings across to some wacky and weird things such as the blue chicken on the top left. And in my final couple of years, I had a bit of a move towards retrofit and low carbon design, things like that. I've now been at the ISTRUCT for about 2 years, and my focus here is primarily around carbon, but also the sort of broader sustainability picture that sits alongside that, both in terms of guidance and standard setting for the membership. Right, I'm going to play this, hopefully this 4-minute video. The reason why I want to play is twofold. One, it should bring some of you sort of up to speed if it's the first time you've given this topic a lot of thought in any depth. And secondly, it's because this is available on YouTube for you to send to other people. So if you've got other people who you interact with and you want to try and convince them that this is a topic they need to start taking seriously, this could be a really quick and easy way for you to do that, to prompt a conversation with them. Like I say, it's only 4 minutes long, so it should be of use for that. I just remembered that when I shared my screen, I did so without clicking audio. So I'm just going to reshare it with sound. There we go. I'm going to mute myself and play the We are experiencing record-breaking storms, droughts, fires, ecosystem collapse, climate migration, which has been brought about by human-induced global warming through years of excessive greenhouse gas emissions, including that from buildings and construction. As these storms and droughts and fires become stronger and more frequent, they will have a larger and larger impact on our lives. What are you going to do about it?
We will exceed 1.5 degrees global warming around about my 40th birthday, bringing previously unprecedented heat waves to Europe almost every other year. By the time I'm my grandma's age, the world will be 2 degrees warmer, locking in as much as 4 metres of future sea level rise and destroying every beach you've ever visited. Our families and friends are looking at a future of yearly weather cycles, currently thought of as once-in-a-lifetime events. And the financial cost will be measured in trillions of dollars per year. We must prevent this future from happening.
Almost 40% of the world's greenhouse gas emissions are due to buildings and construction. I'll try to put that number into perspective. Most of our personal decisions could be quantified in terms of kilograms of carbon emissions. So if you skip a steak, you save 30 kilograms of carbon. If you avoid flying from London to New York, you save 800 kilograms of carbon. But in comparison, when the engineers, architects and client worked together to save this 1950s building from demolition and enabled its reuse as a high-spec office space, we saved 13,000 tons of carbon. That's the same as 16,000 flights from London to New York. Imagine the impact that could be made if we started making reuse decisions like this on every project. We must take our professional responsibility seriously if we want to make the biggest impact we can on global emissions.
The climate crisis presents not only a threat, but also an opportunity. An opportunity for me, for you, for all of us, to make a significant difference to the future of life on this planet. We can't afford to indulge ego and gratification. It's time to move away from taking pride in being the tallest, the longest, or the most heroic. We can do so much better than this. This is an opportunity to create buildings and infrastructure which, by being the smartest, the leanest, the most regenerative, will make a positive impact on the world. Not just for today's generation, but for every generation after. The Institution of Structural Engineers and our partners across the industry are providing the tools and guidance necessary to do all of this. Our profession has never been better equipped to reduce carbon emissions, and it's never been more important than now.
At the institution, we've been working tirelessly to put sustainability on a par with our enduring commitment to life safety. But for lasting change to happen, this needs all of us. The whole industry needs to raise our game. To drive the change we need to see, each of us must commit to something bold, and we must do it now. It's not the detail that's important, it's the ambition, the level of transparency, and the ability to track progress and strive for improvement. It's time to commit to doing things better.
Global warming will affect us and every single generation that follows us. So when you are asked by your children and your grandchildren about the role you had to play during the climate emergency, what will you tell them? I still hate hearing myself speak, but there we go. Like I said, I'll share the link for that afterwards if anyone wants to use it to prompt this sort of conversation with clients and architects and others. So that I mean, in effect, that's a very brief canter through what I'm going to speak about for the first sort of half of this presentation before I move on to giving you some resources and stuff from the institution. But I want to take sort of 15, 20 minutes now to dig a bit deeper into some of the messages in that. And I'm going to start by talking about the difference between 1, 1.5 and 2 degrees of temperature rise, because these are numbers that are just sort of thrown around quite a lot these days, and I don't think we always understand quite what they mean. So as a reminder, we're currently globally on average at about 1 degree hotter than the planet was pre-industrial revolution. 1 degree doesn't sound like very much, but that's about where we're at, 1 or 1.1 or so. And there's a lot of talk about 1.5 degrees as being this sort of target to try and cap global warming to. Now, 1.5 degrees, flood risk around the world doubles. So it's not exactly a perfect outcome, flood risk doubles, but at 2 degrees, it practically triples. So there's a huge difference between 1.5 and 2, just in terms of flood risk. And this is average. So if you live somewhere with a higher than average flood risk, this will be more extreme still. And similarly on heat waves, at 1.5 degrees, nearly 700 million people will be exposed to extreme heat waves every 20 years. So that's not a once in a lifetime thing, that's a 4 times in a lifetime type of thing. And these are heat waves on the scale of the sorts of things that kill thousands at a time. But again, at 2 degrees, that goes up significantly, and that becomes about 2 billion people, which by the end of this century will be nearly a quarter of the population of the Earth will be experiencing this every 20 years. So they got this huge difference between 1.5 and 2, and obviously 2.5 or 3 degrees gets more extreme still, and a lot of these predictions are sort of exponential. those are predictions of what happens if we don't manage to get emissions on the downhill curve of a graph like this. So this is a graph of global carbon emissions, and this is not cumulative, this is year-on-year emissions. So as far back as this graph goes, in fact, basically since humans learned how to dig coal out of the ground and burn it for power, we've emitted more carbon and other greenhouse gases each year than we did the year before. And you can see from the sort of global summits marked on this graph that it doesn't really matter how often humanity comes together to discuss this subject, nothing has really changed so far. The trend has kept going up. In fact, actually, if you add up the area under the graph, which gives you your total emissions, what you'll find is that the total emissions since Rio in 1992, which was sort of COP1, as it were, total emissions since Rio is more than the total emissions prior to Rio. So in other words, we've emitted more greenhouse gas into the environment in the knowledge of what that's doing to the planet than we ever managed to do in ignorance of it, which is fairly stupid. That green downhill curve is approximately speaking what the IPCC says we need to do to keep global warming to 1.5 degrees. And I first drew this diagram in 2020, and as you might have guessed, we're nowhere near going downhill yet. We're only going uphill. So the resulting green curve you would then be left with today's version of this is just far steeper still. That's to get to 1.5. Obviously, there's a sort of 2-degree version that's a bit straighter, less of a concave curve, and that's to limit global warming to 1.5 degrees by the end of this century. And so those predictions I was just telling you, they're all for the year 2100, and that can sound really far away, but I think it's worth reflecting on how close that actually is. So this is my nephew. This is Bobby. Baby Bobby was born in 2019. So this means that we're talking about things that happen to this planet when Bobby turns 80. So he'll probably be retired. He might be a granddad. And I'm sure that all of you know somebody of Bobby's kind of age. And I just want you to picture that person for a second and then imagine them on their 80th birthday party. Maybe they're blowing out candles or something. I don't know. They're surrounded by family and friends. That world that they're sat in is a world that we leave to them. And when your Bobby or whoever it is that you know asks you what you did about it, I think you want to be able to turn around and look them in the eye and say that you did everything you could, right? So every decision you make on every project you work on will matter, and it will affect the future for people like Bobby, people who are alive today. And I think that's worth having in the forefront of our mind through the rest of this presentation today and when you go back to work afterwards. So the good news is that whilst that's all quite scary and gloomy, there's quite a lot we can do about it working in this profession. And I've got a bunch of slides now to sort of talk through how this relates to the bigger picture of sustainability, and then digging down into carbon, and then digging down further into structures in terms of impact. So the first thing to note, of course, is that carbon is part of a very big, knotty, complicated picture of this thing called sustainability. And you can't really tackle one of the things on this slide without tackling everything else at the same time. You mustn't forget the bigger picture. All these things need tackling all at once: carbon, biodiversity, equality, education, they're all interrelated. And the more you read about these topics, the more you realize that's the case. But whilst we mustn't forget that bigger picture, we've also got to remember that out of all the things on the screen in front of you, embodied carbon is where the structural engineers' biggest impact can be. And I'll show you why I say that in just a minute. But it's for that reason that whilst I'm going to talk in terms of that bigger picture, it's embodied carbon that we focus on. And you get the same sort of message if you start reading about the UN Sustainable Development Goals. So the SDGs are really, really broad, right? There's 17 goals, and each of them have got a series of targets underneath them. And in total, there's about 170 targets. And that gives you a complete breadth of what the world says that a better world would look like. So there's about 5 million people contributed to writing the SDGs, and every country in the world has signed up to them. So there's really, really big, broad picture. But again, there's two important things on the SDGs. Firstly, actually, is that they all lead back to SDG number 1. They were all written to end poverty. And the realization was you can't end poverty without ending those other, or sorting out those other 16 things on the SDGs too. They're interrelated between themselves in the same way that previous slide was. You can't tackle climate action SDG 13 without also tackling life on land and life below water, which is SDGs 14 and 15. So they're all interrelated. And then that brings us to the second thing, which is that the idea of the SDGs is that people work out where they can have the most impact, and they focus on doing good in that area, knowing that others will be looking after the other SDGs. So again, my sort of contention as a structural engineer is your biggest impact will be under climate action, SDG 13, and things like responsible consumption, SDG 12. Clean water and zero hunger and reduced inequalities, we have an impact on those too, but it's a sort of different flavor of impact. For me, I group the SDGs together like this, just because it helps me understand them. And I guess because I work in the built environment, this is what I've naturally come to. But those two groups at the bottom are those which most closely relate to our sort of day-to-day work, at least from a technical point of view. That's not to say we don't impact the others, but from in terms of technical delivery, it's typically on the bits on the bottom of this slide. And so it's those bits that I argue that we should focus on as structural engineers. And of course, doing so in the knowledge that this has a global impact, this has an effect on those total global emissions, on that graph that's been going up and needs to come down, and therefore on the effects that baby Bobby and the young people in your life will be feeling come the end of this century. So let's talk about emissions, because emissions sit within all that. Right? So globally, buildings and construction contributes to nearly 40% of all energy-related greenhouse gas emissions in the world. So 4 out of 10. And you'll also see that on this graph, actually, after buildings and construction, there's a sort of other construction industry piece. And we also typically have our foot in other parts of this triangle as well, because you have things like infrastructure, which is related to transport, which is therefore related to what you build and where you put it. So you can see that the world that we live in has, by far and away the biggest impact on this graph out of any of the sorts of professions you can enter into. Now, if you dig deeper into this and you ask where structural engineering sits, it sits a bit like this. So it's about 10% of the total, and most of that's in buildings and construction. There's a bit spread about elsewhere. 10% is the figure given by lots of things that I can reference. Global Alliance Buildings and Construction publish a report each year. They say it's about 10%. I think you can prove that it's higher than that. I think it's probably nearer 15 or maybe even 20. And I say that because the concrete industry alone, the cement industry alone is 7 or 8%, and the steel industry is another 7 to 8%. So just those two materials, whilst they don't all end up in construction, those two materials add up to 15%. And I think the parts of them that end up in construction gives you about 10%, and that doesn't include any brick, any timber, gravel, anything else. So I think we're probably more than 10% in reality, but you can sort of justify 10 pretty easily. Sorry, let me just close that. So what does that look? How does that break down? What does embodied carbon mean? Where does it sit under all of this? So we have this term whole life carbon that you might have heard of, and that effectively, that's the emissions related to the whole life of a building. When we say the whole life, we mean everything from mining materials out of the ground, turning them into products and construction materials. So turning that into maybe some iron, therefore some steel, and then eventually steel beams. Transporting that stuff to site, building buildings out of it, infrastructure out of it. Then the whole of the way through the use of that building, turning on the lights, repairing things, stuff like that, and at end of life, demolishing it and getting rid of it. So that whole life gives you a whole life carbon. That breaks down into one of two things. You've either got embodied carbon or you've got operational carbon. And roughly speaking, embodied is everything you can touch. So the chair that you're sat on right now has got embodied carbon related to it. And that embodied carbon includes transporting it to the place where you're sat right now. And it will include maintaining that chair, and it includes taking it away at the end of life. And it's the same for the closest window to you. It's the same for the floor slab that you're sat on. That's all embodied, anything you can touch. Operational is then anything that you can turn on and off, which is sort of everything else. So that's your lighting, your power, your heating, your cooling, your water. And that's it. So it's as simple as that. Stuff you can touch is embodied, stuff you can turn on and off is operational carbon, more or less. In terms of working out how much embodied carbon is in something, it's pretty straightforward. It's probably the simplest calculation you can do as a structural engineer. You need to know how much stuff you're putting in, and then you need to know what the emissions are per bit of stuff. So if you're building a brick wall, you probably need to know how many bricks and what the emissions are per brick. then you multiply them together, and then you need to do the same for the mortar, the same for the concrete and the foundation, so on and so forth. So you add this up for all the materials, that gives you the total. So it's pretty straightforward. The difficulty with it is to do with accuracy, and is to do with what you actually do with that number. So the quality of information for both quantity and carbon factor will increase as you go through the process. Early on, you will have a rough feeling for how much material you need. You know, probably fairly used to talking about these things in rough terms anyway, because for years we've been costing stuff, and QS always wants to know for the bill of quantities. But your carbon factor information will also be fairly rough, because you won't know precisely who you're going to buy your bricks from. So you might have a general idea because of who you got them from last time, or you might know that on average in your country the emissions per brick is so much, but it'll be, you know, it'll be general. And then as you go through the process and eventually you get a supply chain in place, locked in with some contracts, you'll then know the exact carbon factor. And so it's that increase in information as we go that means that it's worth coming back to this sum again and again to sort of like check that you're still on track to get to where you thought you were going. But the other point I made about, you know, what you do with that, what I think is really important to recognize here is that actually the number itself isn't the important thing here. And I regularly say to people that actually, if you can do this to one significant figure, it's probably good enough. The reason you're going to calculate this is to help you make the right decisions. It's not to get the numbers right. So it's so that you can say to yourself, should this be a steel frame or a concrete frame? Which one of those is more likely to be lower carbon given the configuration that we've got, given the grid that we've got and the loading that we've got, which one's likely to be lower carbon? You do a rough carbon calculation of each option and you pick the one that's best, and then you take that one forward. You then say, well, which configuration works better? Is it this beam shape or this beam shape? Do we go for a stronger concrete mix with smaller sections, or a weaker concrete mix with larger sections? So they affect both the carbon factor and the quantity, but you use it to help make good decisions. That's all it's for. The precise number is not the thing that matters at the end of the day. This is to help you use less of it overall. The carbon factor bit on the right of this is the bit that Tessa will be talking about next month, because this is where her research and Alan's research is coming in. They're trying to determine typical carbon factors for structural materials around Africa that you can use so that you can do these sums quickly and easily throughout the design process. So I'm looking forward to sort of hearing her feedback on that. This graph is important because this explains why embodied is of such importance and why we're talking about this right now. Even when embodied carbon isn't the majority of the building's emissions, it will still be the biggest bit of emissions that happens today. So when you build a building, you release all that embodied carbon. You release most of it in one go up front. On this graph, that's shown as 40% of the total. And then through the life of the building, you've got all of your operational carbon as people turn on and off the lights and stuff like that. But that is generally going to go down because electricity grids around the world will decarbonize. And any sort of replacement and repair of things you have to do later on, that will also be lower carbon than it would be today because materials are going to change. So you've got this big lump of carbon at the start that we've got to stop from getting into the atmosphere. And most of that is the structure. It's typically about 2/3 of it's the structure. So you and what you put on your drawings, that's the biggest bit of carbon that goes into the atmosphere on that project at any point in that project's life. And it's typically one or two materials. So it should be quite simple for us to sort of do something about in theory. Now that's sort of the order of magnitude and stuff like that. What does that mean in terms of numbers? So for perspective, a return flight from Johannesburg to Nairobi, that's about 1 ton of carbon, slightly less than 1 ton of carbon. So if you skip that and you take a Zoom call or something instead to your colleague in Nairobi, you save 1 ton of carbon. That's good. 1 ton's quite a lot, right? 1 ton of a moderate sized car would weigh 1 ton. There's quite a lot of carbon dioxide. But this sort of fairly typical steel frame distribution warehouse, when this was built, the structure, in fact, just the superstructure, in fact, just the steel in the superstructure added up to 5,000 tons of emissions. So 5,000 times as much as that one flight. And that will have gone out into the atmosphere in the space of a few months due to construction. That doesn't include the foundations, the ground slab, cladding, the fit out, anything else, just the steel frame. What that means, of course, is that if you could have done the structural design 20% better, whether that's a reduction in frame size, footprint smaller, you manage to convince the client to give you a bit more time to refine element dimensions, things like that. Whatever it is, 20% better would have saved 1,000 tons. And so our job, in effect, is to find that 1,000 tons on every project. And the reason you're trying to find that is for those things we've talked about that green line and about the future and all that kind of stuff. There's a few barriers in the way, and I think it's worth talking about these up front. The one that gets me most annoyed is things like this. If you speak to people about sustainable architecture, they still expect to see something that's covered in trees. But if you do the maths, you find that, well, actually, to build 1 square metre of office typically emits about 1 ton of carbon. And to absorb that same ton from the atmosphere, you need to plant 10 square metres of forest and leave it there for 50 years. So, like, you see the ratio of planting on these buildings isn't even close. So, this perspective or this sort of assumption as to what sustainable looks like needs to change, and people need to understand that this is about real carbon savings, not about planting on the outside of trees. You've got statements being thrown around these days about tallest timber buildings and most ambitious this and longest that, which again, why does it need to be tall? Is that a good thing or a bad thing? Does it need to be tall? Does it need to be built? Should it be made out of timber? Is it definitely lower carbon to have done that in timber than in concrete? Where did the timber come from? What do the transport emissions look like? How much timber have you had to use? What would the concrete option be? This assumption that you build it out of wood, therefore it's better. You have to do the numbers to be able to prove this, and that's why that embodied carbon calculation equation that I showed you is so crucial with this stuff. And then you still have people fixated on operational energy. So a few years ago in central London, this project was unveiled as being the world's most sustainable office building, and it does loads of really great things in terms of operational energy, but then it makes all sorts of mistakes in terms of embodied. So the columns here are about 12 meters apart or 15 meters apart, something you can sort of work out from the balustrade height. And this is a quote from the client, a quote from the engineer about the client. Now, the engineers who worked on this are very talented and they know what they're doing, and they will have designed that building as efficiently as they could. But when you're being told by a client, well, just put things as far apart as we can get it for visual impact, you're off to a bit of a losing battle. And yet this gets quoted as being the world's most sustainable office building. It kind of stands in the way of it. And then the last slide on barriers I've got really is about sort of innovation. And there's loads of great innovation out there. And there's loads of really good, exciting things happening. And we need more of this, right? We need more R&D, and we need to get research onto building sites quicker. But of course, you can ask yourself the questions with this. Do you need a house to be made out of concrete? Even if it's 3D printed concrete, is that necessarily lower carbon than building a house of a different material? Could you build that house out of timber? With mass timber, things like CLT and glulam, did you need it to be mass timber in the case of the building that you're looking at, or would traditional joists have made more sense? Bearing in mind that a joist is 50 mil thick, and then there's a 350 mil gap to the next one. There's a lot of fresh air in that's been filled in with wood when you use a wooden plank like the ones on the screen. So again, you can start to answer all this with the carbon calculations, but you're pushing back against people who are assuming that one thing's lower carbon when it may not be, and we just need to get used to sort of overcoming all that. So that's the sort of the big picture, right? So that's about why this is important, what scale of impact we can have, and the sorts of things that we need to overcome to be able to have it. And that leads on to the rest of this slide deck, which is all about how you go about doing that, how you make those reductions, how you stay in business in a world that's asking for net zero this, net zero that. The first thing you have to do if you're going to stay in business in a net zero world, I argue, is calculate carbon on everything. So the institution has created lots of guidance around this. This is free. These 2 documents on the screen are both free, and they're free even if you're not a member of ours, because we thought they were too good to keep to ourselves. So there's the guide on the left. It tells you how to go about calculating it. It tells you how to treat different materials and so on. And then there's this tool on the right that goes with it. And the tool is basically just an Excel spreadsheet. It's really simple. It follows the same equation as before. You put in the quantities, and then it picks the carbon factors, and it does the maths for you. So this one on the screen was a house that I got asked to take a quick look at for a friend. And it took me about 5 minutes to put in the information I needed because they already had a bill of quantities because they'd already done the design. So that was really quick, and then from that we could instantly start to see, well, you know, there's a huge amount of carbon here in the insulation products that we've chosen. So are there better insulation products? Is there a way to get less? Are we sure that the operational carbon saving through insulating better is worth expending all this upfront embodied carbon on? You can start to have those questions if you do the maths quickly. This spreadsheet as well, it's simple, so it's quick to get into, but if you want to then edit it and change things, with the passwords in there, the password's carbon, because I'm not very inventive. But you can then edit it. And so we've got, there's engineers based in Switzerland who have taken this and made a sort of Swiss version, translated it into French, and they put all the Swiss carbon factors into the back end of it. So it does the maths based on what's more locally applicable. And, you know, off the back of Tessa's talk next month, you should be able to take the sorts of carbon factors that are coming out of that research in Africa, and again, make yourself a more, you know, regional specific version of this. And it's, you know, it's really quick to update because it's in Excel, and hopefully you will know how to use Excel. Once you've calculated carbon, you then need to reduce carbon, like I said before, and we advocate this hierarchy on the screen here. So we start by saying, well, you just need to use less stuff. And then you can start to do some clever things with your specifying low carbon and then do some offsetting. And we argue that if you can successfully use less stuff, specify correctly, and then offset those residual emissions, that is net zero. That counts as a net zero building. Now, this is mostly about how much stuff you use. And the reason why it's about that instead of about doing something clever with your spec is because for the most part around the world, the low carbon versions of steel and concrete that are out there, they utilize materials that have already constrained resources. We don't have any more of them than we use. Well, there's a bit of spare capacity, but not a lot. And therefore, doing clever things with your spec won't make a big difference globally, whereas using less material in the first place always will. So some examples of that, this is a refurbishment scheme, city centre in the UK, where the engineer was asked to look at knocking down a 1960s building and replacing it. And then they were also asked to look at a sort of refurb version with this extension on the left-hand side. And they demonstrated that the refurb, including the extension, was about half the carbon footprint of knocking down and starting again. There's a 13,000 ton carbon saving, 13,000 tons, 13,000 return trips to Nairobi from Joburg. So really significant, not the only reason the client went with the refurb. It was also quicker, it was cheaper. And there's all sorts of height constraints and sightline things and stuff like that. But this is a big part of the story. And now that they picked this, the developer talks about this quite a lot. They're pretty proud of the fact that they are half the carbon footprint of what they would have been. Build clever, you're sort of halfway down that triangle I showed you before, which isn't on the screen anymore for some reason, sorry. The build clever piece, this is about structural configuration. So these two towers on the screen, the one on the left is built in London, the one on the right is built in Taipei, in Taiwan. Taipei has some of the world's highest earthquake and typhoon loading, so you got wind and seismic. London has a bit of a breeze, and that's about it. You hold onto your hat sometimes. But the two towers are about the same height, and they use about the same amount of steel per square meter of floor area. And the reason why, despite the higher loading on the right, it's still the same amount of steel. The reason why is because the architect said to the engineer, what would be the most efficient structural layout of this? And then the architect should follow that. And so that building on the right is about 30% less steel than its neighbour in downtown Taipei. And that 30% saving was only really achievable because this was led by structural configuration rather than other drivers. It's not to say the building on the left wasn't efficient, it wasn't well designed, but it had all sorts of weird constraints in terms of sight lines and things that meant that structural configuration was further down the hierarchy of importance. So you can get sort of, 50% savings from reuse and 20 or 30% from configuration. And then at the bottom of that triangle, on reducing emissions, you then get into your building things efficiently, design, mass design efficiencies, constructing efficiently to minimize waste, things like that. This is your 5 to 10% saving sort of region, I argue. So this is the difference between you putting out a set of construction drawings where you haven't yet done that final sweep through of optimizing element sizes versus one where you've managed to find an extra couple of weeks to do that, and you've trimmed some capacity out of things. So you've got everything down to being nearer to a utilization of 100%. And you're confident to do that because you know that it's going to get built correctly. and you know that the codes of practice you follow have been designed correctly so that 100% utilisation is safe. This is why this is at the bottom of the triangle. You sort of see the decision making behind reuse versus new builds versus the decision making about configuration versus the decision making on getting the last bit of steel work out of your frame side. They're kind of chronologically further along, right? So this is why we draw the triangle the way we do. So it's kind of top to bottom is the same as starting project to end of the project, but it's also big impact down to smaller impact. Doesn't mean that you shouldn't do the things near the bottom. Of course you should do them. You should, and even if you made the wrong decision at the top of the pyramid, you should still do them. But it's just worth bearing in mind that's where your real impact is that stuff at the top if you can do it. Of course, you know, to reuse an existing building, you need there to be an existing building, so it's not always completely feasible. Couple of other sort of little things on, so on loading, don't you dare put any spare capacity into your building on top of what the loading requires you to do, because 5 kPa looks like this up at that end of the room, and 5 kPa plus a factor of safety of 1.5, or whatever it is you're using, depending on where you're working. You know, you have to physically lay people on top of that crowd on the screen to get to 7.5 kPa. So the idea that you then design the floor to only work at 80% utilization doesn't really make all that much sense, does it? Like I say, even if you've made the wrong decisions early on, still lots of decisions left to make. And I think when you pull all this together, you can go around and start to look at the designs of things that's been built already and ask yourself these questions. Why is it a new structure? Why are the columns of space apart they are? Why is it in these materials? Why is it the basement, so on and so forth? There will have been decision making on all of that. And I'm sure that there was some very sound, economically driven decisions behind every single one of those choices. But there's a carbon impact to each of those as well. And if you can do some quick sums, you can tell people what the carbon impact is. You can say new versus reuse, you know, it's 10,000 tons of carbon. Column spacing, 9 meters versus 11 meters. That's 2,000 tons of carbon difference. Are you sure that's worth it to you as a client when, you know, by the end of this decade, you're going to have tenants asking you, you know, how sustainable was this building when it was built? What's the carbon footprint look like? Things like that. So it's up to us to ask these questions and to try and give some sort of metrics to go with them. And the reason to ask them is because of things like this. So this is a project. It's a fairly ordinary residential scheme that a colleague of mine worked on. And he was asked by the client after the building had been constructed. The client said, could you come and do a review of what we built and tell me whether or not we could have saved any carbon in the construction, and do that without changing the architecture or nothing significant. And he could demonstrate that there was a 40% embodied carbon saving that had basically been missed through some optimization, through some material choices, slight design tweaks, and 3/4 of that was cost neutral as well. So had those questions have been asked earlier and the client had that decision-making process earlier during the design, not post-construction, they would have been able to save 30-40% of the carbon footprint of the building. It wasn't being asked, so it didn't happen. So, you know, like I say, those emissions have happened. Getting them back out of the atmosphere is pretty tough. But that's why you keep asking these questions. And if you ever get that pushback of, well, hang on, you know, I don't like the idea of going leaner and leaner and leaner. Surely that's unsafe. Things are going to start to fall down. Then we've written some notes, and when we share the slides afterwards, you can click the links on this. But we've done some bits of guidance from people who know about safety and fire safety and resilience, and they all come to the same conclusion, which is that if you undertake your design in a careful and considered manner, if it's to code, if you're a competent engineer, if you're given the time to do your job properly by the clients, then there's no reason why you shouldn't be able to design everything to 100% utilization, you know, lean design all the way through, if you've done that job competently. That's the conclusion they all come to. So it's not about saying, well, we're going to lose material and that's unsafe. But it is about saying, look, if we are going to, you know, lose material, we need to be doing this job well, and I need to be given the client, be given the time by you, please, clients, to do my job well. Okay, last bit, and then we're going to move on to questions. I've just got a few slides on what we've been doing at the iStruct about all this, because we've generated quite a lot of guidance of 3 things that will help you, and we've also gone some way to trying to set the standard a bit higher within our membership. So on standards, kind of 2 ends of the spectrum on this. One of them is to do with the awards. We used to celebrate things for being tall and long and, you know, big scales and things like that. That's gone now. As of this year's awards, the criteria for greatness, as it were, are these 4 Ps on the screen, these 4 attributes on the screen: planet, process, people, and profession. That's because we recognize that a good structure contributes towards something that is, you know, it's efficient. So in terms of its planetary impact, it's low. Yeah, it's useful for people. In terms of its social impact, it's high. You know, the processes behind it are at the top of the game in terms of technical excellence. You know, are you pushing the boundaries forward in terms of how you design, how you construct, things like that? And then in terms of profession, the 4th bit, you know, are you doing this in a way that's collaborative, that shares with the wider profession? Does it increase our understanding and the sort of respect we have from the wider market? And that's how we're going to judge projects from now on. And these 4 projects on the right of this slide were all award winners last year, and they would all have been award winners again this year based on the new scheme, because they kind of exemplify those attributes. So we're raising the bar, we're raising the standards in terms of what we have as our sort of like highest level of achievement. At the other end, then when you've got your sort of base level, what do we expect of chartered engineers, which is your entry level, and that's being updated as of next year. So these updates have been signed off, but it won't be implemented till next year, and there's more information about this online. But in essence, you're going to be required to be able to calculate and talk about and design for embodied carbon as a core skill. This is not an extra, this is not somebody else's job, this is our jobs as engineers from now on. And that comes in as of next year. So we're going to raise the bar in terms of that minimum requirement. And we're happy to do all that because we know that we've generated the guidance that's needed to help engineers to do this. This PDF, you can get this off the internet on that link on the top right. It's got about 150 articles linked into it, which is quite a lot. We've put some recommended ones in there to help you find them easily, and you can search within here if you use Control and F, and all of those titles are clickable. So you can click video, carbon in concrete, steel and timber at the top of that recommended reading, and it'll open this in your browser. About half of that's free if you're not a member, and the other half that you'd need to be a member to get all of it. It'd be cheaper for you to become an affiliate member than it would be to pay for all of those, I suspect. But yeah, a good half of it also is free if you're not to. So, you know, there's loads of guidance out there. If you want to learn about how you decarbonize concrete, on how you use timber efficiently, how you reuse, how you strengthen what you've got, even all the way down to how you influence the clients to try and go with you on this stuff. We've written guidance on it now. You can go out there and find it. We've produced guidance alongside this that's for those people who are maybe lecturing, giving presentations, writing articles, things like that. Again, you can get hold of this. We haven't made this exclusive to those people. So there's a 6-page PDF or something at the link on the top right that just gets you to start asking questions of yourself about, you know, what would the sustainability opportunities be for the topic that I'm writing about? Do I understand them? Could I explain them to the people who are listening to me? What if they ask me the difficult questions about reuse or about lowering the impacts? What will I say for that? And then lastly, in terms of written guidance, at least, there's we're gonna publish this new guide at the end of this year or maybe early next year that will talk about circular economy, which sounds like a fancy term that no one really knows what it means, but really it's just to do with reusing what we've already got and designing so that somebody in future can reuse what we've designed. So it's got these 4 chapters or 4 parts to it that are on the screen. And you'll see that number 2 is reusing whole buildings. Number 3 is about reusing components, parts of old buildings. And then number 4 is designing so somebody else can reuse your structure that you've designed. And that would really help, because that means you can then get through that quicker route to halving the carbon footprint of what you've designed by using things that are readily available. And even if it's just a bit of steel work from the old building, it's like you do the top story of the new building or something like that, it all adds up pretty quickly. And then last but not least, and this is the last slide, and then we'll go to questions. Last but not least, we've produced some formal training courses as well. So we've done 2 of these. There's something called Embodied Carbon Basics, which is what this screenshot is of, and you can access that entirely electronically. If you're a member, you just search it in the on the website, and it'll take you to it, and you can just click access now. And it's basically a series of short videos with some quizzes in between to test your understanding. And you can do a CPD test at the end and get a CPD certificate. I think it's about 4 hours worth of CPD in total. And that'll take you right through the basics. So you've got a really good grounding, and that's the level that we're setting people's expectations at for the chartered member exam, for example. So if you've got through this, you'll be able to deal with the embodied carbon aspects of the exam. And then the second link on the page is something called Net Zero Structural Design, which just goes deeper. We teach you how to come up with creative solutions for, coming at a brief from a different angle, proposing new versions of briefs to clients, advocating for change, things like that. Those courses have sold out every time we've had them so far, so we know they're quite popular. But do check them out on the website if you get a minute, or drop me an email and I'll point you in the right direction.